Today we are going to discuss molecular orbital theory. See, you all are familiar with the word covalent bond. You know what is a covalent bond? It is a bond formed by mutual sharing of electrons between two atoms. Now, the thing is, thanks to the chapter structure of atom, you are aware that basically atoms exist in orbitals, and every orbital has an electron wave function associated with it. Now, suppose there are two atoms about to participate in a covalent bond. Let's say two hydrogens are approaching each other to form a covalent bond. Now, the electron wave for this hydrogen, let us say the electron wave is like this, and the amplitude of the electron wave is represented by the symbol psi, that is written as psi, pronounced as psi. So psi a is the amplitude of electron wave of one of the hydrogen atoms. Now the electron wave for the other hydrogen atom, let us say it is like this, and the amplitude is psi b. So psi a and psi b are the amplitudes of the two electron waves. Now when the two atomic orbitals overlap, then the resultant electron wave is obtained by the addition of the two amplitudes. So psi a plus psi b gives the amplitude of the resultant electron wave. So this electron wave represents the electron in the orbital of this hydrogen. This one represents the electron in the orbital of this hydrogen, and this we say represents the molecular orbital, the orbital formed by the overlap of the atomic orbitals. Now such a molecular orbital is known as a bonding molecular orbital. Bonding molecular orbital is considered to be stable, and if the two electron waves are in this manner before they overlap, then the overlap of these two will give a resultant whose amplitude is psi a minus psi b. So when the two atomic orbitals overlap, the overlap may happen in this manner. In that case, the molecular orbital is called bonding molecular orbital, or it may happen in this manner, in which case the resultant amplitude becomes psi a minus psi b, and the orbital is called anti-bonding molecular orbital. So it is called anti-bonding molecular orbital. Now these two are both available for the electron to occupy, but the energy of anti-bonding is higher than the energy of bonding. Bonding is considered stable, relatively anti-bonding is unstable. So in terms of electron filling, the electron will first occupy the bonding or molecular orbital, and only then it will go to the anti-bonding molecular orbital. Now the thing is that you are aware that this is how we represent s orbital. So when the two hydrogen atoms approach each other and their atomic orbitals overlap, then the overlap can be represented like this. So this is your molecular orbital, and this is known as sigma bond. This is called a sigma bond. There is another way of obtaining a sigma bond, that is by the overlap of a p orbital with an s orbital. This is also a sigma bond. And of course, as you would expect, it could be that there is overlap of two p orbitals. And this is also another type of sigma bond. So whenever two s orbitals are about to overlap, the overlap can be represented like this. It is called a sigma bond. When a s and a p are about to overlap, we get a sigma bond of another kind. And when two p orbital overlaps, then also we get a sigma bond. So these are the different ways in which you can get a sigma bond. Now what happens is that in the p subshell, there are three orbitals. So let us say if we call this one as pz, then px and py can overlap laterally. So if they overlap laterally, the molecular orbital, this is called a pi bond. So this is called a pi bond. So the molecular orbital can be represented like this, and this is called a pi bond. Similarly, if you have pz, then also they can participate in a pi bond. So the diagram will be somewhat similar to this. So pz can also overlap laterally to form a pi bond. So this is also an example of pi bond. So when two p orbitals overlap laterally, you will get a pi bond. So depending on whether the overlap of the orbitals is head-on, like in these cases, or it is lateral, like in these cases, for head-on we call it sigma bond, and for lateral we call it pi bond. So these are the broad categories of bonds, sigma bond and pi bond. Now in the second period, the elements are lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon. Their molecules are expected to be Li2, Be2, B2, C2, N2, O2, F2 and Ne2. Now it is found that the molecular orbital energy diagram for these is of a particular kind and for these is of a different kind. Now the thing is, the molecular orbital energy diagram for these molecules is like this. So first you have one s overlapping with one s to give sigma 1s and sigma star 1s. Then you have 2s overlapping with 2s to give sigma 2s and sigma star 2s. Then you have the overlap between the p orbitals, which can happen in these ways. Now, this one is pi 2px, this is pi 2py, this one is sigma 2pz, this is pi star 2px, pi star 2py, and this is sigma star 2pz. So this is the molecular orbital energy diagram for the elements from Li2 up to N2. So pi 2px, pi 2py, sigma 2pz, pi star 2px, pi star 2py, and sigma star 2pz. So this is the molecular orbital energy diagram for the elements from Li2 to N2. Now, in case of O2, F2 and Ne2, this part is the same. This part is the same, there is no difference. But for the rest, there is a difference, and that is you first have sigma 2pz, after that you have pi 2px and pi 2py, then you have pi star 2px and pi star 2py, and finally you have sigma star 2pz. So if you are considering the molecules O2, F2 and Ne2, then the orbital energy diagram begins with sigma 2pz, then pi 2px, pi 2py, then pi star 2px, pi star 2py, and then sigma star 2pz. So that is the basic difference between the energy diagrams of molecules up to N2 and O2, F2 and Ne2. Now, keeping this molecular orbital energy diagram in mind, let us try to analyze the electronic configurations of some of these elements. So we begin with H2. Now H2, you know that every hydrogen atom has only one orbital, that is 1s. So the orbital of one hydrogen has one electron, and similarly the other one has also one electron, and when these two overlap, then we basically get both electrons in a single sigma 1s orbital. It is formed by the sigma bond of these two. So sigma 1s, and it contains two electrons. Now what happens is, when two hydrogen atoms approach each other and the atomic orbitals overlap, so we count this as one sigma bond, or basically one covalent bond. Now the number of bonds is also called bond order, and there is a way to do it mathematically. It is half the difference between bonding electrons and antibonding electrons. So bond order, which is equal to the number of bonds, is half the difference between bonding electrons and antibonding electrons. So you can see that in this case the bond order is 1. Second thing is, you will notice that both the electrons are together as a pair. Whenever that happens, we say that the molecule is diamagnetic. In other words, it does not have any net magnetism. So this is the electronic configuration of H2. Now let us consider helium. Now in helium what happens? These two orbitals overlap to give a sigma 1s orbital and sigma star 1s orbital. So you can see that sigma 1s has 2 electrons and sigma star 1s has 2 electrons. So in this particular case, and incidentally we are talking about helium. Now in this particular case, the bond order is coming half of 2 minus 2, which is 0. But if bond order is 0, that means between these two heliums there cannot be any bond, which means that He2 molecule cannot exist. So He2 molecule is hypothetical and in truth it does not exist. Now let us consider Li2. As you would expect, the sigma 1s and sigma star 1s apart, in Li2 you will have 2s also. So I am doing one thing, I am directly going on to the 2s. So in the sigma 2s orbital there will be 2 electrons. So the bond order, the total number of bonding electrons will be sigma 1s has 2 and this has 2, so 4, and anti-bonding is 2. So the bond order is 1 and without any doubt it is diamagnetic. So Li2 molecule is diamagnetic. So after we have completed 1s, as usual, let us go straight away to 2s. Now in the 2s, sigma 2s there will be 2 electrons, sigma star 2s there will be 2 electrons. So bond order, there are 4 bonding and 4 anti-bonding, so bond order is 0. That means beryllium 2 molecule is hypothetical, which means beryllium 2 molecule does not exist. So beryllium also, the answer is that it does not exist. Now let's move on to boron, that is B2. Now in case of boron, you will appreciate that now the p orbitals will enter into the picture. So for boron, after you have completed 1s and 2s, we move on to the p orbitals. As you are aware, in boron there is 1 electron in the p orbital. So when you are writing down the configuration, you have to follow Hund's rule. That means there will be a molecule in each of these. So what will happen is that the bond order will be half. Now prior to this you had 4 bonding, so now it will be 6. Anti-bonding will still be 4, so bond order is 1. And for the first time we have encountered a molecule which is paramagnetic. Now please remember, the paramagnetism is because of the 2 unpaired electrons. These 2 electrons are unpaired, and that is the reason why the molecule is paramagnetic. Now let's move on to C2, that is carbon 2. If you follow Hund's rule, after the filling up of single electron in pi 2px and pi 2py, there will be filling up of the next electron. So basically what will happen is that the bond order will be half of 8 minus 4, that is 2. So the bond order of C2 will be 2, and it will be diamagnetic because you can see very clearly that there are no unpaired electrons. So C2 will be a diamagnetic molecule. Now let's move on to N2. For N2, if we continue from where we did in carbon, after the filling up of pi 2px and pi 2py, next will be filling up of sigma 2pz. So the bond order will be half into (10 minus 4). So the bond order is coming equal to 3, and you can easily see that it is diamagnetic. Now, using the fact that the next molecular orbital is available, but we are not using it right now, that is pi star 2px and pi star 2py is available. Let's have a look at some other species which are related to N2. First, let's look at N2 plus. Now, the bond order of N2 plus will be half of 9 minus 4, that is 2.5. Then let us have a look at N2 minus. So the bond order will be 10 minus 5, that is also 2.5. Then have a look at N2 2 minus. So the bond order will be half into 8 minus 4, that is equal to 2. Now you know that bond order is equal to number of bonds. So if there are more bonds, it will be more stable. So the order of stability will be N2 greater than N2 plus, greater than N2 minus, greater than N2 2 minus. But the question which may come in your mind, why is it that N2 plus is more stable than N2 minus, because both have the same bond order? So the answer will be that in N2 plus you are using one antibonding molecular orbital less. In case of N2 minus, you are using this antibonding molecular orbital, whereas in N2 plus you are not using that. You know, more antibonding molecular orbital means less stability. So that is why the order of stability will be N2 greater than N2 plus, greater than N2 minus, greater than N2 2 minus. Now let's move on to the next three elements, that is O2, F2 and N2. So if you recall, we had discussed that the diagram will be a little different for these three. So for O2, you know that the configuration is 1s2, 2s2, 2p4. So there will be 4 electrons in the 2p subshell, and your energy diagram will look like this. So sigma 2pz, pi 2px, pi 2py, sigma star 2px, sigma star 2py. So the first thing that we can comment is the bond order. So the bond order is going to be half into 10 minus 6, that is equal to 2. So the bond order of O2 is 2. So this means that there is a double bond, and interestingly O2 is paramagnetic. You will notice that there are 2 unpaired electrons, so O2 is paramagnetic. By the way, you know that the next orbital available is sigma star 2pz, but we are not using it. Now keeping this in mind, let us try to find the bond order of some similar species. Let's begin with O2 plus. So O2 plus, the bond order will be 2.5. Then the next, let's take O2 2 plus. So O2 2 plus, the bond order will be it will be 3, because half into 10 minus 4. Then O2 minus, now please note O2 minus is called superoxide ion. So O2 minus will be half into 10 minus 7, that is 1.5, and O2 2 minus, that is called peroxide ion, half into 10 minus 8, that is equal to 1. So these are the bond orders of O2 plus, O2 2 plus, O2 minus and O2 2 minus. When you compare the bond orders, you will see that the order of stability is O2 2 plus greater than O2 plus, greater than O2, greater than O2 minus, greater than O2 2 minus. So how do we explain this order of stability? Very simple. O2 2 plus has a bond order of 3, so it is the most stable, followed by O2 plus, which is 2.5, O2 is 2, O2 minus is 1.5 and O2 2 minus is 1. So this is the order of stability of species related to oxygen. Now let us have a look at the energy diagram for fluorine, that is F2.